All right, here's one last example of a particle, like an electron, under the influence of a step potential. But in this case, what we'll have is not an infinite square wave, but a finite square wave. So in this finite square wave case, we'll call this energy here U equals 0, and also the total energy equals 0. And so the finite step potential drops down by a factor of U. Here we can say U equal to, let's say, 2 eV. Let's say the energy of the particle is 4 eV. Okay? And so in region 1, as it moves along, all of the energy is kinetic. When it gets to region 2, we have the kinetic energy plus some potential energy. Okay? And so this means then that this potential energy function, because it drops negative, is going to cause the particle to speed up even faster. So you could imagine this like a mass that's moving along like this, and then it goes into a ditch like that. Okay, it's going to be going even faster because that potential energy is turned into kinetic energy. So it's going to go faster here than it was here. And then it comes back out on this side, and then it's going to slow back down to its original value. And so that's what we're going to expect up here. We would expect a particle to have a wavelength in region 1. That's essentially what we got before for a particle that isn't under the influence of a potential. And we can call this x equals 0. And then we can say the wavelength is going to shorten in this region because it's going faster. And a faster particle means a smaller wavelength, because the velocity, mass times velocity, remember, is h over lambda. So the velocity is equal to h over m lambda. So with a higher velocity, we have a shorter wavelength. Okay? Because here, we're going to be dividing by a smaller number. So that gives rise to a larger velocity in region 2. So it's going to be going faster. And then when it comes back out, it's going to slow back down to its original velocity, but with a lower probability, because it's got to make it all the way across this barrier potential, and some of the energy will be reflected. And so in this case, then, this is going to be lambda 3. And lambda 1 will equal lambda 3. This is again region 1. This is region 2. This is region 3. This is x equals 0, x equals L. This is lambda 2. This is lambda 3. Lambda 1 equals lambda 3. Okay, so in region 1, we have the same kind of solution as before. Psi 1 is equal to a e to the I k1x plus b e to the minus I k1x. And so k1 will equal square root of 2m e over h bar. And that will be equal to k3 for the exact same reason that we were able to show that this was true in the previous problem. In region 3, psi 3 is equal to e to the I k3x, where k1 equals k3. So this is k1, that's k3, and so the particle, if it is able to make it through this barrier, and doesn't look much like a barrier because it's actually speeding the particle up, how could that make it reflect here? Well, classically it can't, but quantum mechanically, anytime you have a difference in the properties of a wave, this here, I didn't have this set up. This should start there. So it should be like this until it gets to here. And then it should get smaller until we get to there, and then it should get larger again. So this is your lambda 2. Okay. And so then that picks up again to its value on the other side, but quantum mechanically it can reflect on this boundary, can reflect on that boundary and have an infinite series of reflections within here, and then some of that probability we'll make it through the barrier, and so we'll have a lower amplitude on this time, but with the same velocity once we measure the particle. Okay? And so solving the Schrodinger equation then is still necessary for this problem. But we did it in the previous example, and it's an identical calculation to the one that I would do here, and so I'm not going to repeat that. But you would be expected to repeat it on an exam if I asked for the full solution to the Schrodinger equation. You need to show why this is the solution to the Schrodinger equation, which is exactly the same thing that I showed in that previous example. Okay, and then K2 now will equal the square root of 2m times E minus U over h bar, just like before. But now U is a negative value. Nu is minus 2 eV. So that's what makes this a plus, which makes for a larger value for K, makes for a smaller value for lambda. So this is equal to then, in region 2, psi 2 equals C e to the I k2x plus d e to the minus I k2x. These are still oscillatory functions, which means that there can be some reflection that happens on each one of these boundaries. And K2 be equal to the square root of 2m, 9.1 times 10 to the minus 31 kilograms, times, and here's where you want to be careful, because this is 4 eV, this is minus a negative 2, so it's actually 4 plus 2. So that the difference between them gives rise to more kinetic energy and therefore a lower wavelength. So it's going to be 4 plus 2, or 4 minus a negative 2, times 1.6 times 10 to the minus 19 joules per eV. And then that's divided by h bar, which is 6.63 times 10 to the minus 34 joule seconds. And then that's divided by 2 pi, which brings the 2 pi up to the top again. And so this is just like what we did before. The only difference now is that this K2 is going to be not 4 minus 2, but 4 plus 2, or 6. Okay, so let me knock that number out. So that's going to be 1.25 times 10 to the 10. And that's per meter. Okay, so that's the value for K2. K1 is going to be equal to 2/3 of that value, square root of 2/3 of that value. And that'll be equal to K3. But here, I'm just going to do the K2 calculation. And so K2 is equal to 2 pi over lambda 2. And so that would be 6.28 divided by lambda 2 equals 1.25 times 10 to the minus 10. So we can take the, for lambda 2, just take the reciprocal of that, multiply it by 2 pi. This is plus, wait, that's plus 10, sorry. This here has got to be plus 10, not minus 10. Minor difference, factor of 10 to the 20. The k is a big value, but k is 2 pi over lambda, so that makes the lambda a small value. And that's what it's showing here in the calculator. I just wrote it negative in my head. All right, so I'll take the reciprocal of that. 6.28 times, and that gives me 5.8 times 10 to the minus 10. Meters for lambda 2. Then I can get a velocity in region 2 that's equal to h, 6.63 times 10 to the minus 34 joule seconds divided by mass of an electron times the wavelength, 5.98 times 10 to the minus 10. So just the reciprocal of that. Divided by the mass of an electron. And that gives me 1.45 times 10 to the 6 meters per second. Okay, so that's a little more than 1/100th the speed of light. Okay, because 3 times 10 to the 8 is the speed of light. This is 10 to the 6, so that's 100th the speed of light. So that's actually 1/200th the speed of light. It would be the velocity of the electron in region 2. Then you could do the same thing by finding this value for K1. You could find lambda 1 and go through and find that. And I'll leave it as an exercise for you to find V1, which is equal to V3. From K1, just following through the same kind of calculation that I did here with lambda 2, you can do the same thing with K1. It's just the square root of 2me over h bar, and then say that's 2 pi over lambda 1. And then you can write mv equals h over lambda 1 and find v1, just the same way. Okay, so, and the reflection and transmission coefficients are, at least in outline, they would look the same as before. They wouldn't be the same because the algebraic solution would be different. But the transmission coefficient would still be E star E divided by A star A. And the reflection coefficient would be B star B divided by A star A. And so, at least in outline, with the solutions looking much the same way they did before for psi 1, psi 2, and psi 3, was e to the I k3x, we would have solutions that, at least in their basic functional form, look the same. That when you actually plugged in and got your 4 equations, you would have a completely different algebraic solution, even though this particular form looks the same. The algebraic solution would be quite a bit different.